What's the difference between a junior paper, a senior thesis, and a PhD? Well, the junior paper, your advisor points out a mistake in the literature and you go and correct it. For the senior thesis, you go into the literature yourself, find a mistake and correct it. For the PhD, you make your own mistake.
Can you tell us about the origins of your work on the Kervaire Invariant?
Terry Wall gave a lecture, and he had just created non-simply connected Sergei, which was a fantastic achievement that he had done, really wonderful piece of work. And he never mentioned my original theorem in the non-simply connected case. And so I got terribly angry, and I said the only way to penalize him for this is to show his theorem is wrong. Well, his theorem was perfectly right. But in trying to prove that it was wrong, I discovered a different approach to the Kervaire invariant, which was much better than the theorem that he didn't mention. So that was the one instance that I know of a theorem generated by anger. That's one of the three things that I'm proudest of.
And of course, ultimately it led to the solution 3 years ago of the so-called Kervaire invariant conjecture. Going back to your greatest contribution, of course, was topology of high-dimensional manifolds. How do you see the present and the future of high-dimensional manifolds?
Well, topology of manifolds has got to move across some border.
To algebraic geometry, maybe.
Algebraic geometry is possible, but new venues to develop algebraic methods.
One of the things I remember you doing as a PhD advisor was you tended to have a view of students as using the right gears or the wrong gears by telling them things like you're working too hard or you're not working hard enough.
While you do have to be obsessive to do mathematics, you also have to keep a perspective in what you're doing and having a relaxed approach. If you don't have a relaxed approach, you'll miss some important things going by. You don't look to the left and right.
You have to be prepared to zoom in and zoom out.
Yes.
There's a lot of luck involved in this business. Let's face it.
Bill, you have a very interesting family background. What would you like to tell us about that?
Well, my father was the leader of the Communist Party of the United States for many years, from approximately 32 to 45. And I was born, I should say, in 1934, very soon after my mother arrived with my two older brothers from Russia. So she was Russian Jew. And so there we were, and I was brought up in a third-floor apartment in Yonkers, New York, with my two brothers and so forth. And so this rather prominent family began to affect us more and more as time went on.
How do you feel that affected your development?
Well, we always felt very special. And this specialness, of course, was partly due to my father and partly due to my brothers, because my brother Felix, who was 6.5 years older than me, was a child prodigy. And he had read The Decline and Fall of the Roman Empire by Gibbons at the age of 7, and later was reputed to have read the Encyclopedia Britannica from cover to cover. But I think he forgot a few details, though. But and so he went through school ahead of us, and then came Andy, who was 2.5 years older than me, and then me. And so when I arrived in school, very often the teacher would hear my name and ask, was I related to Felix or Andy? And if I said yes, I very often detected a glint of fear in her eye. It really paved the way easily for teachers were well intimidated, and with extra hints from Andy on how to intimidate them further.
Well, I wanted to remark here that all three brothers became mathematicians. Yeah. Can you explain why all three of you went into mathematics?
It's not at all clear. I originally was interested in physics, and I didn't even know what mathematics was. But physics I had learned about basically from the atomic bomb in 1945. I used to read science fiction, and then when they dropped the atomic bomb, I realized science fiction, but they were all pikers. The reality was unbelievably more than anyone had dreamed of in science fiction at the time. And I read in the New York Times a complete description of the construction of the bomb and the physics behind it, and U-237 or 235, I guess it was, and et cetera, et cetera. And I thought this was fantastic. I was going to be a physicist.
I remember hearing from friends who knew your family that one of the things that was considered odd about your family was that your mom gave you a fairly normal upbringing, despite being in the notoriety of your father's position,
right.
Actually.
And she was kind of notorious among the other communists for not sending us to communist camps and not taking us to communist meetings and so on.
Not having
she wanted us to have a kind of normal upbringing.
Not the usual red diaper experience.
Not the red diaper experience. Right.
Did either of them have a mathematical interest at all, or
No. But they were very logically oriented.
Your father was such a commanding personality, and people can't help but note that you and your brothers all chose a profession which feels about as far as from his concerns as one could imagine.
Well, it's hard to account for, but I can tell you how it happened to me.
Yes.
And well, I went through the schools in Yonkers, and then I went to MIT, where both my brothers had gone. And I wanted to do physics, and I thought that was the most exciting thing. I'd read this very exciting book when I was in high school by Einstein and Infeld called Evolution of Physics, which gave the most beautiful kind of popular exposition of things like quantum mechanics and relativity and all these Gedanken experiments, as they were called. It was just fantastic. I thought, this is really great. Physics is for me. Then when I got to MIT, I found out that wasn't the way you did physics. That was the way they could describe physics that way, but that's not the way people did physics. And in particular in the lab, I was absolutely hopeless in the lab.
Your love of chaos did not stand you in good stead there.
Yeah, well, I was just incompetent, basically.
Well, actually, one other thing which I wonder about, which is, in a certain sense, did your father's experience impose kind of a double, though, isolation on your family? In the first instance, because from the general society, because being a communist was no small issue in those days, right? And then when he was expelled from the party in the late 40s, you must have been cut off from a lot of people that your family was close to at that point.
It was very dramatic. One day we had 100 friends, and the house would be full of visitors, and the next day, nobody. One or two stragglers occasionally come, but it was a striking experience.
I think you and I went over once some speeches of Mao, where your father, who I remember well, Mao gave two speeches about your father, one praising him to the heavens, and then a few months later denouncing him to the bottom pits.
Yeah. And everybody was following the line.
Right.
And my father refused to recant his positions that he was being attacked for, and he was expelled from the leadership and then expelled from the party. And then he went to Moscow to find out what was really going on. And of course, I didn't realize it at the time, but he was very lucky to come back. Yes. But I didn't know that at the time. And he went there and sat and finally got an audience with Molotov. And I don't know what they said exactly. And he came back. And they gave him the position to act as agent for Russian publishers in New York, which he did for a while. And I think there was not much money in that at the time. But somehow, I don't know, he got some investors, whatever. But that didn't work for very long. And then he went further and further away from the communist line, and eventually wrote books about how Marxism did not apply to America.
Yeah, I remember you gave me one of those.
Yeah, I have a pile of them still at home. It was not a bestseller, but...
Wasn't a much better living than being the Russian publication agent, I imagine.
No. It was a very hard time financially,
Yeah,
basically. We had family, 2 uncles and an aunt in the New York area. One of them, in fact, lived up the street, and they all helped us financially. And then Felix got a job, and that helped financially. And this was very good. Felix went to MIT and got out in 2 years, and then he went to Princeton, got out in 2 years, and got a job. But he had a very hard time getting, of course, a permanent job. But at least he had a job, and that he was the one in our immediate family that had a regular job.
I remember you once said you were worried about yourself being able to get a job ever.
Yeah, right. Well, when I left Princeton in 1957, in April I was invited to Rochester, gave a talk, and they said, well, we're going to give you an offer, you'll get the official letter in a week. And it didn't come in a week, and much time passed, and finally, in August, my advisor said, oh, don't worry, I'll try and get you a job at Cornell. But then I got the offer from Rochester finally, 4 months later, the one that should have come in a week. And I went to Rochester, I had nothing else, and then I met one of the trustees at a reception for
Trustees
of Rochester, at a reception for new faculty, and he explained to me what had happened. And my appointment had been kicked up the administrative level until it reached the Board of Trustees. Now, this was just an instructorship in mathematics. This is an insignificant thing. You write the name in a line and that's it. But they were all so worried about my father, who was 12 years out of the Communist Party by that time, and anathema to the Communist Party, in fact, but nobody seemed to know that. But he was a symbol. And so everybody was scared stiff of doing this until it got to the trustees. And they had a knockdown, drag-out fight in the trustees, and eventually Linowitz and his people won, and that was the trustee, Saul Linowitz. And
I remember one resonance of this when you told me years later, when you went to China, they were nervous about your father also.
So he was a pal of Zhou Enlai, in fact. He didn't know Mao very well, but Zhou Enlai he considered a friend. And he'd spent years in China.
Bill, well, you said you went to MIT as an undergraduate. Yeah. Do you want to tell us that experience and sort of how you got into mathematics from those experiences?
Well, so I went to MIT and full of enthusiasm for physics, and I took the standard freshman curriculum, which is an elementary physics course, and that was fine, and elementary chemistry, it was okay for a while. And then a routine calculus course, and then the second term, a rigorous calculus course. And the physics course was fine, except for the lab. I wasn't very good in the lab. Okay, well, and this calculus course was absolutely beautiful, the rigorous calculus course given by Witold Horevich. And so that was really good. Now, I should point out that I had been taught calculus several times by Felix when I was a teenager, but it didn't take. But it was not did not immunize me from calculus. But then when I saw a real course in it, I was quite pleased with the whole thing. But I was still interested in physics. And then in the sophomore year, it really went to pieces. And I remember the lab was much more difficult, and I couldn't do the dry lab, which I used to do, of course, just writing up the experiment without doing it. And I was just totally incompetent. And then I also had this course in classical mechanics. And suddenly I realized, listening to some of the other students, I realized that I didn't have that thing. The really good students had something called physical intuition, and I did not have it. And the rest of the course somehow was ridiculous. It was matrices and computations, and I was taking a linear algebra course where everything was done beautifully. And there they were in physics, really screwing up everything. And by the end of that course, which I got a C finally, I decided mathematics was for me, no more physics. I really fit in mathematics. I didn't fit in physics.
Other math courses there at MIT that...
Yeah, of course. Then I took a lot more math courses. Yeah, but about that course in classical mechanics, the teacher was Victor Weisskopf, and he gave me a C. And 40 years later, I met him at a birthday party for one of my colleagues, and he walked up to me and said, Browder, and shook my hand. Could he remember 40 years later a student he had given a C to? I couldn't believe it.
What other courses did you take in mathematics?
Well, then I took some modern algebra course, first a linear algebra course.
Who gave them?
First course I took in algebra was given by a man named Kohn, who died at a very young age. And then I took some analysis courses, and then I took a modern algebra course from Iwasawa, and who later became my colleague at Princeton. And I found that very, very charming. It was a very, very beautiful course. And the way he graded the papers appealed to me very much, because instead of putting a grade A, B, C, or D, or giving a number 97 or 35, he drew a pie chart. And so if it was a perfect circle on the top of your paper, it did not mean 0, it meant perfect. And then he would remove a chunk of pie according to how much he felt you'd mistaken. So I thought this was emotionally a much better way to express his opinion of the paper than some artificial number. It was kind of anti-digital, if you want.
What about topology?
Well, I took an introductory topology course from Jerry Waschnitzer, who was later also my... that wasn't very good, but it was it was chaotic. But I learned quite a bit about the mechanics of topology. And then I wrote my senior thesis with Iwasawa, which was a very good experience because he gave me Pontryagin's book to read, Topological Groups, and then assigned me to write a paper. He also gave me a paper on compact rings that some Japanese whose name I don't remember, compact topological rings, and told me to generalize it to locally compact. So I did it and wrote a thesis and a little piece of research and defined what was probably cohomology of some kind, but I didn't know it at the time. So that got me interested in this relationship between algebra and topology. How much more you could say about algebra when you had topology.
How did you decide to go into graduate school in mathematics?
I could see my brother Felix, although he was having a hard time getting a job, a permanent job, he still was making a living. So I was assured that perhaps at least I could make a living doing mathematics. How would I have done it in some other science? Well, maybe I could have and maybe I couldn't.
And why did you choose Princeton?
Well, Felix again had gone to Princeton, and it had such a reputation. And the idea of the freedom of the Princeton graduate school appealed to me very much. The idea that no grades, you didn't have to go to the courses if you didn't want to, you were completely free. And I thought that was a wonderful way to do it. I was against and I still am, against all these artificial restrictions.
Backtracking just a bit, how did you choose MIT?
Well, my two brothers had gone there, first of all, so I knew I had a path there. I was pretty sure I'd get in. And then I examined Princeton and Harvard, and they both required chapel. And I was not going to go to a college that required you to go to chapel, I can tell you that. So I'd crossed them off the list. But Columbia did not say anything about chapel, and so I applied to Columbia also. And I got in, but I decided to go to MIT. I'd heard so much about MIT, and I was convinced. And it was a very good choice.
And did you find the transition from undergraduate school to graduate school very smooth?
No, not so much. Not so much.
In what ways?
Well, the first year in graduate school, it was hard for me to do topology. There was a course being given by a visiting professor, but I think both Steenrod and Moore were on leave that year.
What year was that?
That would have been 1954, 55. There was a visiting professor giving a course in an algebraic topology, but it was really more elementary than I needed. And then there was a course in algebraic geometry, was also given by a visitor, which was okay. There was a course by Artin in number theory, which I was very excited about for about 6 weeks, and then discovered that I didn't have the foggiest idea what was going on, but he was such a great lecturer that I forgot it. But then when I realized that I didn't have any idea what was going on, then I gave up that aspect of algebra. And my only exciting course really was Feller's course in a completely different subject, in functional analysis. But he was so dynamic a lecturer and very chaotic as well, and it was very interesting. But of course, I learned something, but it was not what I was basically interested in. So, but the following year, then everything went better. Moore was back, then Steenrod was back. There were several really exciting courses in topology.
Did you have interaction with Lefschetz also in those days?
No, I didn't. He was retired by then, and he was interested in differential equations at that time.
Right.
Yeah, he was seen around the department, but I didn't have any interaction with him at all.
Who were the other graduate students interested in topology in your year?
Well, let's see. There was Dick Swan. Jim Stashev came a year or two later. I think a year later, maybe. And then there were older students. There was Frank Peterson, Emery Thomas, and they taught me a lot. I learned a lot from both of them, and just talking in the common room. And that was the great thing about Princeton. You didn't have to rely on the professors to learn things from. The students would really give you an education. And they would give it to you in maybe a slightly different way. They would say, if so-and-so is on your general's committee, here's what he's going to ask, and here's the answer. It was a very nice group of people.
And did junior faculty also play a role in that for you?
Yeah, well, John Moore was junior faculty at the time, and I was listening to his course, and he became my thesis advisor.
What about Jack Milner?
He would give an occasional seminar or a course that was just fantastic, just unbelievable. So those were the three that really did my education. Moore was my advisor. Steenrod, who gave some splendid lectures in basic algebraic topology, but really very, very well developed. And Milner.
So you were a graduate student when Milner discovered the exotic spheres.
Yeah.
Were you aware of his work on that immediately, or did it take some
Well, it was the talk of Fine Hall, but I didn't really, I didn't know why exactly.
Can you tell us about your thesis, work on your thesis, how that developed?
Yeah. I was working on homology of loop spaces, basically, which was then slowly becoming a big subject of interest. Sergei's thesis and some of his other papers had really done a lot about that and skimmed the cream off the top, and then it became a question of really going deeper into it. And Moore gave me a paper of Kudo-Noraki, which defined homology operations in loop spaces and mod 2. And the operations would be defined, if you had an nth loop space, you could define n operations. Now this was in contrast to the Steenrod operations in cohomology, where they were all there. And so, but Kudo-Noraki defined the mod 2 very much like Steenrod's first definition of cup I products and so on, and enabled them to calculate the homology mod 2 of iterated loop spaces of the sphere. And so it's a very beautiful paper, but it was done with the old-fashioned Steenrod approach. And so Moore suggested I put it into Steenrod's more modern approach. And that wasn't hard to do. And then I proved some other little theorems about loop spaces, like loop spaces of finite dimensional H spaces. I proved the obvious theorem. And then Moore gave me this fantastic idea of an algebraic machine involving Lie algebras and so on that would calculate a lot of homology of loop spaces. And he asked me if I could work it out. So, well, I didn't do too well working it out. I couldn't get too excited about it, probably because it was his idea, and I felt what was my contribution? And it really inhibited my work on it. And then, just before I went to Rochester, he found out that the idea wouldn't work. And so I didn't have that thesis. It would have been a great thesis, but it wouldn't have been much mine. The fantastic idea would have been his, but it didn't work. So I went to Rochester with no thesis, no degree, and they noticed. They noticed at Rochester. They were not happy. They were not happy. All right. So I felt a little uncomfortable about that. But then I discovered that Cornell had been ready to make me an offer to rescue me from my plight at not getting the offer from Rochester. And then when I accepted Rochester, they stopped and didn't make me the offer. But they were willing to do it again. So, and they made me an offer. There I was with no thesis or anything, and they made me an offer of instructorship. And I felt so much better that I sat down and wrote a thesis. And it was very interesting because I sat down, I said, my gosh, it's a pity to go another year without a thesis. I'll just sit down and write everything I can about what I've been doing. And so I wrote up my version of the Kudaraki operations, and I suddenly noticed in the middle of this, when I wrote it up in this more equivariant way, that there was another operation there with all coefficients corresponded to commutator products in the first loop space. And in the nth loop space, you had something which was a manifold suspension of a commutator product. And so that enabled me to generalize their work, Kudaraki's work, to arbitrary suspension, but all mod 2. And then, inspired by a paper of Moore about the second loop space, the other half of my thesis, I managed to prove a cockamamie theorem about the homology of n-fold loop space of an M-sphere with coefficients of mod p, provided p was, I think n was less than p, some crazy theorem like that. But it was quite an elaborate algebraic argument. And that half I never published, but the other half I published. And so that was my thesis.
One point which, while I was your graduate student, and I remember you always emphasized about writing clearly, writing out what you knew, and what you're mentioning here seems part of that kind of philosophy.
Exactly.
I want to elaborate on that.
It taught me that the writing can be part of the research, that you'll see things in the writing that you won't see but just thinking about it abstractly. And without actually formally writing it down, you might miss something. And so that was a very instructive experience.
Steenrod was very intense about that theme, that writing it down was part of the process of clarification.
And writing it down well.
Yeah.
Well, what is the statement? Write it so that 10 years later you can read it and understand it yourself.
You can understand it yourself, right?
You only spent 1 year at Rochester.
Right. And then I moved to Cornell, and that was a whole different thing. At Rochester, I had nobody to talk to about topology. There were many good mathematicians there in other areas. Paul Cohen was there, who later won the Fields Medal, and the Rudins were there, and Arshad Hajian was a very good measure theorist. He was there. He and Paul Cohen and I had come at the same time, and we talked to each other, but there was nobody to talk topology with, in particular algebraic topology. Well, Mary Ellen Rudin, of course, is a very good points topologist, but That was not my dish of tea at the time. So, but at Cornell there were lots of people, and Paul Ullem and Peter Hilton was there.
Oh, yes.
He was there for visiting my first year, and he gave a very beautiful course.
The voice alone is worth the price of admission.
But he was a master lecturer and so beautifully organized. And he was very good at finding the essence of something and pulling it out and using it.
He was a radio personality before there were television personalities.
Well, I tangled with him once many years later at his 60th birthday in St. John's. We were invited to have a little panel discussion on television about education. And so we had a nice discussion for 3/4 of an hour or something like that. And then, just before the program ended, he said something so outrageous that I was beside myself, and the program ended. I couldn't answer him. He was so skillful.
What did he say?
Oh, I don't remember exactly. The issue basically was the role of research for teachers of mathematics, and I was in favor of it.
Of course.
And he was rather negative at times.
He did spend a lot of time afterwards
About education.
About education.
Yeah. He did a lot about that. Yeah.
How long were you at Cornell?
5 years altogether. 1 year I was on leave, and that was a very good year. I got an NSF postdoc, and that was 59, 60. And I was going to go to Oxford to study with Henry Whitehead. And then it turned out that Henry was going to be at Chicago in the fall and Princeton in the spring. So I went to Chicago in the fall, and then I went to Oxford in the spring when he came to Princeton. And that was very interesting. It was very interesting to meet him. He was quite a colorful personality. His initials, of course, were JHC, Whitehead, which many people interpret as, Jesus, he's confusing. He was not noted for the clarity of his lectures, but he had very deep ideas in topology.
Yeah, some of his ideas feel like they were way ahead of their time.
Absolutely, yeah. He had the founding idea of K-theory,
Yes,
basically.
absolutely.
Yeah. But K1 rather than K0, which was interesting.
While you were at Cornell, you started something which I believe is still going, the Cornell Topology Festival. How did you realize you just do it once and it took a life of its
It
own?
must have been 1962, since this is the 50th anniversary. Well, we were there, and let's see, who was there in 62? Well, Ullem and Roger Livesey. And anyway, at the end of the year, we noticed that there's still a lot of money left in the grants. And we hadn't been able to convince enough speakers to come during the year. So I said, why don't we just bring them all here, bring a whole bunch, and we'll have a Topology Festival.
I remember once going up there with you in the 60s when there were all kinds of demonstrations and campus was occupied, and we had to go to that in secret. Actually, we had to go through some tunnel underneath to get to the math building. So we couldn't be officially present on the campus. We had to sneak around.
Really?
Yeah, those are interesting times. Wow. Yeah.
You came from Cornell to Princeton. Do you know who in Princeton hired you, so to speak? Was it John Morley?
I suppose it was everybody.
Yes.
Yeah. In the 59-60 year in Chicago, I had proved my first really good theorem, which was the theorem that if you take an H-space, and an H-space is just a space with a continuous multiplication with unit. Well, this became a thing of great interest because of Hopf's theorem around 1940 that showed if it was finite dimensional and an H-space, its cohomology was an exterior algebra. And that had been generalized by Borel to mod P to say that the cohomology was a tensor product of exterior algebras and polynomial rings, truncated polynomial rings. And so it became a question. The Hopf's theorem, of course, applied to Lie groups, had already been done by hand by Élie Cartan showing using the whole Lie group structure and maximal tori and so on. And he'd also proved, so he'd proved that it was an exterior algebra, and he'd also proved that the second homotopy group of a Lie group was 0. And so after Hopf's theorem, it became a question, for a finite dimensional H space, would the second homotopy group have to be 0? So then I proved that, and by proving a very strong theorem about the torsion in the homology of an H space, and related to the Bach-Stein spectral sequence. And it was a very neat little lemma that I got about the next Bach-Stein. If the first Bach-Stein was 0, then the next Bach-Stein had to do something.
The Bach-Stein spectral sequence.
Bach-Stein spectral sequence. And then a very elaborate technical argument to boost it up to proving that.
So this was 1960.
That was 1959, in fact, in the fall of 59. So I did it in Chicago, and I remember Whitehead was very pleased with that theorem too. And Frank Adams wrote a very nice review of my paper, my announcement. So I felt very good. I felt like I had done something substantial. My thesis, I thought, I was very happy with my thesis because it meant I would be able to work for a living. And it was okay. But this was something that other people had tried to do and not done, and I could do it. So I felt very happy with that theorem, and I'm still happy to this day with that paper. I thought it was one of my best papers.
So this study of finite dimensional H spaces must have been your transition into questions in surgery also.
Eventually, yeah. Because that same paper in which I proved that pi 2 is equal 0 and all that, at the end, just as a kind of a footnote or appendix, I proved that a finite dimensional H space satisfied Poincare duality. And I mused that everyone would have liked to prove that finite dimensional H space was a Lie group up to homotopy and maybe some copies of S7 or P7. And at least I proved Poincare duality. So I speculated in that paper, perhaps one could prove that they're actually manifolds if you couldn't prove that they were Lie groups. Well, then I had a paper with Spanier where I proved that a finite dimensional H space is self-dual, which meant that the top homology was stably spherical. And then in 1961, I was in Berkeley, and Kervaire gave a beautiful series of lectures exposing the paper of Kervaire and Milner on groups of homotopy spheres. And I saw surgery for the first time. And I went back to Cornell. I said, I wonder if I could use that to prove that a finite dimensional H space is a smooth manifold. And it turned out I could, to almost all, a big chunk of that. I could prove it with that. But it actually gave me a general theory of when a space would be the homotopy type of a smooth manifold. So
A simply connected space.
Simply connected, right.
Your talk at Aarhus in 1962 was about that, of course.
Yeah.
Why wasn't that talk published until very much later, even though it was obviously important?
It's an interesting question. Well, there it was in the Aarhus proceedings, after all.
Yes.
When I was working on H spaces, I was very young, and I thought, oh my God, I better publish this right away. Somebody else is going to get this result. And later, of course, I found out nobody was even reading my papers, much less trying to prove the same thing. So I got a little bit relaxed about publishing quickly. And then suddenly I got this theorem, and I was very happy with that theorem. And I think that was one of the main things that got me the appointment at Princeton, certainly. And I was lecturing to my students in Princeton and so forth. And of course, later I realized that everybody was working on it. At H-space days, nobody was working on it. Of course, at the same time, there was Novikov.
Yes. How did you first hear the name Novikov? Do you remember?
Well, of course, I'd heard about his work on boardism, cobordism, yeah. And then I was going to the Stockholm Congress, 1962, summer of 62, and I had lectured about my theorem about homotopy type at Aarhus and at Bonn. And then when I got to Stockholm, one of the Russians who came, and there were very few Russians that were allowed to go to meetings, international meetings outside of Russia. And one of the Russians who was allowed said, well, there's this paper of Sergei Novikov, and maybe would you be willing to read it for him since he can't come? And I read it, and wow, it's very similar to what I had done, except he had the opposite point of view. He was trying to classify manifolds of a particular homotopy type, and I was trying to prove that bizarre things like H-spaces were manifolds.
You were complementary.
Yeah, so we were kind of complementary. So afterwards, we went to Moscow. We had planned a tour to Moscow, in fact, to visit one of my aunts as well, who is still there in Moscow. And we met Novikov.
Did you speak Russian with him?
No, I don't speak Russian.
Oh, you don't speak
Russian? No. So we worked with broken English on his side.
So this would have been around when?
This was 62.
62. I remember he came and visited you.
Yeah, 67, yeah. That was a lot of fun, yeah. And of course he came with his, what would you call him, a partner. They wouldn't send a single person alone out of the Soviet Union. Minder. It was not exactly a minder, because he was a respectable mathematician. What's his name? Kostrikin. He was an algebraist, yeah. But they thought if they sent them in pairs, they would take care of each other, and of course the spouses remained at home and so on. And so he came with Kostrikin, but then they were willing to go off by themselves once they got there. And Kostrikin went one way, and Novikov was in Princeton for a while, and then we took him to New Orleans to go to a conference in transformation groups in New Orleans that spring. And it was very funny because there were such strict regulations about Russians. We had to get special permission from the State Department to go away from New Orleans, or to go to New Orleans in the first place. And then there were special restrictions about you shouldn't go further than, I've forgotten, the radius in New Orleans, and so forth. Okay. And so we were there at the conference, and at some point Novikov said, well, this is getting a little boring. Why don't we go and see the countryside? I said, okay, great. We'll rent a car, and we'll drive around and see some things. So several of us got in the car, and we drove along. And we were driving out along the Gulf Coast, and we started to joke. Well, let's see, it's 20-mile radius, I think. Have we gone 20 miles? No, we haven't gone 20 miles. And we kept driving. Have we gone 20? No, we haven't gone 20 miles. And so then we stopped and decided to walk on the beach for a little bit. Then I saw a helicopter coming, and I said to Novikov, look, here comes the State Department looking for you. And the helicopter came right up next to us and then flew back. But that was all I ever heard about it. So nobody took it too seriously, I gather. But that was very nice to meet him. Yes. But that, of course, was the time that Sullivan had just done a lot of his work, and Novikov was very interested in that. And so he grilled Sullivan very, very thoroughly.
That wasn't the first time he grilled him.
Oh, that was the first time he grilled him, yeah. And in Sullivan's original version of the Hauptvermutung, there was an error, and he had missed the four-dimensional K invariant, the significance of the core.
The Rochlin invariant.
The Rochlin invariant. He had missed this, and so his theorem was much weaker than, and I guess that made a deep impression on Novikov in particular.
He's still complaining about it.
Bill, you had a number of very well-known students, especially in the 60s. Can you tell us a bit about the atmosphere here at Princeton with all those students and young faculty here?
Oh, it's very exciting, very exciting. I remember my first course in Princeton, my first graduate course in Princeton had this fantastic array of students. There was Dennis Sullivan, Jack Wagner, Santiago Lopez de Medrano, George Cook, in the fifth one, and Norman Levitt. And they were all my students at the same time. And that was unbelievable. It was unbelievable. And of course, Sullivan was unbelievable. I mean, the Sullivan seminar is now famous for how long it takes and how much Dennis squeezes out of the speaker. And I was the first Sullivan seminar. I was single-handedly Sullivan seminar. He really worked me like a dog. So there was the other way around. He was supposed to work your students like a dog. He worked me like a dog. But it was a lot of fun. It was fantastic fun.
How would you compare the atmosphere among topologists in the 60s and 70s? Has it changed much?
I remember in the early 60s, Frank Peterson and I sat down and listed all the algebraic topologists in the world. It was pretty easy. We got to up about 50. By 1962 or 60, 63, 62, 63, there were a fantastic number. Exponential growth has been taking place. But still it would probably less than 1,000. And of course it's continued since then. And at some point in the 70s, they had a hard time getting jobs, and they were going to all kinds of lesser-known universities. And I made the remark that there was no town of more than 50,000 that didn't have a Chinese restaurant and an algebraic topologist.
What about people working on the same subject in the kind of competition? Yes, has that changed?
Oh, yeah.
Yeah.
It really did change. It was like a friendly little club in the late 50s and 60s and early 60s. And then suddenly there was an element of serious competition and a few personalities that came who were very, very competitive and very, very good at competing.
You can if they have a name them exactly.
Frank Adams and Terry Wall in particular. And I remember the Seattle...
63.
Was that 63?
Yes.
Yeah. And that was really a very different atmosphere. And because of them, because they were so, well, they were so vigorous,
Yes.
but also very, very competitive. So it was quite interesting. It was quite interesting. But not the chummy little club that it used to be.
So that class you had with those students that you were referring to, that would have been 1965, I guess, 66?
No, that would be 60, 64, 65. That was the first class I taught, 64, 65. Sullivan and all the rest.
Oh.
Yeah. So that was very interesting. And so that went on for many years, that I got an enormous number of great students.
There are two sitting here.
Yeah, for example. And you were 66?
Yeah, I came in 66. And you were giving like the second year of a sequence on algebraic topology and geometric topology.
Yeah. And you came in 85? 82.
He's a kid.
Yeah. And by then, I was interested in more algebraic things. Yeah. Greek homology, yeah. But I remember the early years, there was Frank Quinn and Mike Friedman and Lou Kaufman and Stoltzfus.
Yes, Stoltzfus.
And many others. Just so many. And then it kind of the culmination, I guess, came in 1970, when Siebenmann had finished his thesis with Milner, and Kirby arrived at the Institute from Chicago, and that kind of was the icing on the cake for surgery, proving this 50-year-old question. Was it more than 50?
Well, I think Siebenmann had finished his thesis earlier.
Yeah.
When I came to Princeton in 66, I think he was gone already.
I think he was gone, yeah.
You came back. You spent a year also in France in the...
67, 68.
Yes, 67, 68.
In time for the revolution.
Yes, right.
Which caused surgery, a chapter of your book, I believe.
Well, I don't know whether I could describe it to that. But it was supposed to have one more chapter, yeah.
So that was around the period you did the work on the Kervaire Invariant.
67, yeah.
67.
Yeah.
Can you tell us about the origins of your work on the Kervaire Invariant?
Well, that's an amusing story. So I guess it was 66. There was a month or 2 months of topological activity in Geneva, Switzerland. Heffliger was the main guy. Terry Wall was there, and many others. And I remember Terry Wall gave a lecture, and he had just created non-simply connected surgery, which was a fantastic achievement that he had done. Really wonderful piece of work. And then he gave this lecture, and he was proving some theorems which were generalizing my theorems in the simply connected case, and he was generalizing to having a fundamental group. And he never mentioned my original theorem in the non-simply connected case. And so I got terribly angry. And I said the only way to penalize him for this is to show his theorem is wrong. And so I went to work to try to prove his theorem was wrong. Well, his theorem was perfectly right. But in trying to prove that it was wrong, I discovered a different approach to the Kervaire invariant, and that led to my paper on the Kervaire invariant, which was much better than the theorem that he didn't mention. So that was the one instance that I know of a theorem generated by anger. Well, a lot of theorems are generated by envy, say, or various other things.
Not many by lust.
Not many by lust. I'm sure there are a few cases.
Yes.
Is it the one you're proudest of?
I mean, that's one of the three things that I'm proudest of. So my paper on H-spaces, Pi 2, the thing, Novikov, Browder Novikov thing, and that paper. I think are my three best papers. And the Kervaire invariant is probably the best, really. And whereas the other two papers were completely out of the blue, in that nobody was really else was really thinking in these directions, which was a good thing. But the paper on the Kervaire invariant, there were a lot of people thinking about it. Yeah. And Brown and Peterson had done this very nice special case of dimensions 8k plus 2, and so on.
And of course, ultimately it led to the solution 3 years ago of the so-called Kervaire invariant conjecture.
As the interest began to shift towards a non-simply connected case, you did some foundational work on reinterpreting some non-simply connected problems in various clever, simply connected ways. Yeah. Some of those things you also did with on interpreting things in geometrical ways that allowed you to reduce the simply connected cases. Some of that you did with, of course, with Roger Livesey, and some with Jerry Levine.
Yeah. That was the year I was at the Institute. Yeah. And there were 4 papers that we did, which was all about codimension 1 surgery. That was the thing.
This was mid-60s, 66?
64. Yeah. So there were 4 papers. One was I wrote by myself. It was called Structures on M cross R. Park Van Cam Phil Sock.
It was very important for Novikov for his proof of the topological invariance.
Yeah, and Kirby used that there in particular in his paper on annulus conjecture. And then there was Livesey and I. He was my colleague at Cornell. We never, and we went to each other's seminars, but we never worked together. Then we were studying fixed point free involutions, and when you had the obstructions to getting a sphere of codimension 1 invariant under this involution. And then the paper with Levine on fibering manifolds over a circle. And then the 3 of us about putting a boundary on open manifolds.
That was very much
what Siebermann then picked up.
And that led to Siebermann's thesis.
Exactly.
Right. Yeah. And of course the Browder-Levine, that led to Farrell's thesis.
And ultimately that got used by Shanison in his thesis on Z cross G.
And I think he used a paper with Livesey, the fixed point free involutions.
Thinking about that paper and about generalizations of it is part of what led to my work on with Julius on Shanison on nonlinear similarity.
So that was a year's work basically with this collaboration, which developed all those ideas in codimension 1 surgery. So that was a very good year. So when I talk about my favorite papers, that's my favorite year.
So which year was that? That was
63, 64 at the Institute.
And that was at the Institute?
Yeah, yeah. And the end of it was in Cambridge, but
Or Zeman organized it.
yeah. And that was a lot of fun too. And then I had a little paper with Hirsch about Sergei and PL manifolds.
Yes, of course.
Yeah. And nobody ever refers to that paper.
It's not entirely true, but I'm at least aware of it.
I thought it was very interesting because it's a slightly different point of view. Once you expose that point of view, everybody thinks it's very simple. But before that point of view, maybe it isn't so simple.
All of PL topology has become somewhat, well, passé is perhaps too strong a word, but no one works in PL topology anymore.
Well, it's not distinguished from topological topology,
I know it isn't.
really. I mean, it's too well integrated into the larger subject,
Possibly.
and it's really, and the results have a more complete look in the topological setting, and then
Exactly.
the PL setting is done as a modification of that. often.
Well, there's some point in doing topological manifolds. PL topology doesn't have a really. I was very interested in what Novikov had to say at your 60th birthday conference about Kervaire and Ziemann. This is the work which you said was the icing on the cake of surgery theory. Was indeed a great achievement in 1970.
I think Kirby's annulus conjecture theorem was published as a separate paper in the Annals. And that avoids all the technicalities of Kirby and Seidman, which makes the book so long and so forth, and exposes the wonderful torus trick of Kirby.
How easy is it?
And I think Novikov likes his torus trick very much, as he should. But it's a little different from Kirby's. Kirby's is a step further.
How easy is it to jump from Kirby's paper to handle body decompositions, say, of topological manifolds? I mean, I'm told that Kirby's paper is very good and very important, but it's not enough. You cannot just use that.
No, you can't.
So you have to
You've got to use a lot of technology.
Yes.
Yeah. So, but I always loved the basic idea, the kernel idea, the really new thing, and that was this torus trick.
I think you spoke about it in Missouri, your colloquium lectures. You had someone published it.
This reminds me of one of your general points of view, which is that what matters in a series of developments is the results that change point of view, and that's very difficult to keep track of. You always pointed out because
In retrospect, you forget that there was a different point of view, or there lacked a point of view.
Once your head has moved to a different place,
Yes.
it's hard to imagine what the difficulty was.
Exactly, and Eilenberg was really very, very good at that. We were talking about Eilenberg at lunch, and he was very, very good at taking a new point of view that really exposed things in a different way, and afterwards you say, well, yeah, of course. But up to that point, nobody had seen this.
Right.
And so it was very, very important.
Yeah, well, he went from being my main undergraduate teacher to you being my main graduate teacher. I went from one to the other. And indeed, that's very true of him.
Like inventing obstruction theory. That was
a great.
afterwards you say, well, how else would you do it? But of course, how would you think of doing it first? I mean, and that was a fantastic thing.
Or even think about the interplay between fundamental group and homotopy groups, which was also his. The action of pi 1 on pi n.
Tell us a bit about your book, the experience of writing a book, and the kind of the difference between the contribution in a book form from the papers.
My surgery book was really just an account of my lectures, written carefully. And but I put a lot of organizational work into that, and a lot of, again, point of view, like the way I did the Kervaire Invariant obstruction was very different there than it had been done before, and and very much related to my Kervaire Invariant paper.
One unfortunate aspect of your book, I must say, it came out too late.
I know.
You know this, of course. That's
Getting slow there, yeah.
yes. I mean, this,
in what sense?
Well, Wall's book had already come out
Yes.
with the non-simplicate. He was quick, oh boy.
yes. Oh, yes, he was. Absolutely.
But he was quick, but he was complicated.
Yes, but it did kind of overshadow for beginners like myself in 1970. I had Wall's book, you know, and I had to learn from that. I would have been very happy to have learned from your book, but I didn't have it.
I think you wanted at some point to expand it to include more of your work on embeddings, which is very beautiful results. I guess that was your Moscow International Congress talk,
sure.
but it didn't make it into the book.
That's
It's sort of the missing chapter at the end.
But you know, my Moscow talk, it's very interesting because it appears, the paper appears in the Moscow proceedings, but it doesn't appear in the table of contents. Yeah, some funny glitch. So if you look for it in the table, it's not there, but the paper is there. It's very funny. Yeah.
It was part of the elimination of the references to Browder in the
I
Soviet
think
Encyclopedia.
so. I fear that there is some truth to that.
Can you say a few words about how you got into topics like transformation groups, algebraic K-theory?
I was invited to go to this transformation group conference in Tulane. And so I started thinking about how to apply surgery to transformation groups. And of course, the free case had been done, some nice applications by Wuzhong Shang and
Terry Wall. The actions of cyclic groups, for example.
Yeah, I think it was a little later, though.
That was one of the motivations for Sergei, for his developing non-simply connected was exactly.
So then I wrote an expository paper, but then I found that I could expand the expository paper to a research paper at the end and create a lot of actions and using surgery theory with fixed point sets and so forth.
This led to your theory with Frank Quinn.
Yeah, a little bit later, yeah. So then I started getting more and more interested in transformation groups, and first S1 and was the one I looked at in the Tulane Symposium a lot. And then gradually I finally conceded that finite groups would be a good thing to look at. Finally I started to get interested in homology of groups, and I saw Gunnar Carlson's paper extending Smith theorem to products of spheres of the same dimension. And I saw a very easy way to prove those.
This was more like 75, mid-70s.
It's about 83, actually.
Much later.
82. And that got me started thinking much more algebraically. And, yeah.
We've kind of skipped going back about Borel's work. Did that influence you, Borel's work?
Oh, yeah, very much so. Well, first of all, his thesis with all the calculations, the cohomology of the classical groups and so on, and the classifying spaces of the classical groups, and the wonderful spectral sequence arguments, very difficult spectral sequence arguments that he did. He was a fantastic spectral sequence technician. And then, of course, his paper on Hopf algebras. So he generalized Hopf's result on Hopf algebras over fields of characteristic 0 to fields of characteristic P, in particular Z over the field with P elements, P prime. And whereas Hopf would get an exterior algebra on odd-dimensional generators over the field with P elements, you would get polynomial rings truncated at some height of power of P in a tensor product of things, as well as exterior algebras over odd-dimensional generators. So, and I thought this was a very beautiful theorem. So I was working on H-spaces at Cornell, and I one time came down to Princeton, and I went to see Borel and tell him about all my new theorems about Hopf algebras, and I was writing lots and lots of Hopf algebra papers at the time. Spectral sequences of Hopf algebras. That was a wonderful paper because I had a spectral sequence for the first term of a spectral sequence for the first term of a spectral sequence. I was very proud of that. Nobody noticed, but I was very proud of it. Anyway, I came to talk to Borel and tell him about some of my things. And I was talking to him, and then there was a knock on the door, and there was Andre Weil. I don't remember.
Where is this? Was that
At the Institute. I don't remember Weil's exact words, but what I heard was, "Get rid of this jerk and we'll go to lunch." And Borel said, "I'm busy." And I loved Borel ever since. So I had always a very good relationship with Borel. We were editors of the Annals together for many years, and there was a lot of mutual respect, and he was a very straightforward person, sometimes too straightforward for some people's taste, but he was a very good colleague.
You know, the lady who this very nice lady who used to help put out the Annals.
Fanny Rosenblum?
No, earlier than that. Anyway, she told me that Borel, as editor, used to sometimes, when those days letters had to be typed up, she would write, "Dear," turning down a paper, "Dear Professor so-and-so," he would cross out professor and write in doctor. And if he didn't think so well the person, and then she felt bad, she couldn't send out a letter like that, she would retype it. But there were times when he crossed out doctor and wrote in Mr.
Elena Weisenbaum, maybe.
Yes.
Elena.
Yes.
Well, that was a lot of fun in many ways, being editor of the Annals. I recommend it to anyone who wants to lose friends quickly.
I remember I was at the birthday lunch for Walter Neumann, whose birthday is very memorable. It's on the 1st of January. And at noon, you looked at your watch and you said, "Ha! I've just stopped being an editor of Annals." And you could see the relief flooding your face.
I think you once described it as, if you accept the paper, they say, well, of course, because it's the greatest paper there is, right?
Yeah.
If you reject it, how can they reject it if it's the greatest paper on earth? But maybe you want to say a bit more about your experiences, because you were editor for quite a long time.
Yeah. It's January 1st, 1982.
1982 I stopped.
So there's sometimes been controversies between the editors, right, over the years.
Oh yeah. Well, I missed some of the best ones. When
Right,
I was
some
editor,
of them preceded you.
it was pretty tranquil. But the earlier days, there were some tremendous fights.
And resignations, even, as a result.
Yeah, there's a famous story about the days when editors were Andre Weil, Don Spencer, and Norman Steenrod. And there was a paper that Steenrod wanted to accept and Weil wanted to reject, and they couldn't agree. And so Spencer tried to bring them together. Now he said, well, let's go out for lunch and settle this. Now, there were two alternatives for lunch. The best restaurant in town was Layer's, and they wanted to go to that. And the worst, the grungiest restaurant in town was the Balt, which many awful descriptions of it, which was also very cheap and economical, and where Steenrod wanted to go. And they couldn't agree where to go, so they couldn't go to lunch, and they both resigned. And I think then Milner and Borel became editors after that.
But in your time, it was pretty peaceful.
It was pretty peaceful. It worked pretty well. It was interesting, but it was a lot of work, and we did lose friends.
Lose friends simply because people took rejections personally?
Exactly. But it was always difficult to reject a paper of somebody you knew. And but I have more regrets about papers I accepted than papers I rejected.
I remember once being in Bill's office, and he was looking at some paper that needed repeated revisioning by, I won't say by whom it was, after it had been accepted. And there it was, and Bill was trying to work his way through this, and he looked up and he said, "You think you could reject a paper after it's in galleys?"
you have any advice to give for people who want to publish a paper? What are the things you would be looking for to make it a good candidate for publication?
Of course, the content should be of interest, but people don't write it well enough for they don't think of the reader so much. They think of their result and how wonderful it is and how they savor it and so on, and don't write enough material to make it understandable to the audience. This is standard disease. I think it's getting better. I think the standards of writing are improving over the years, but that's the most common mistake.
Well, the standards may be driven up simply by the fact that it's more competitive to get papers into the top journals.
There's more respect for good exposition now than there used to be.
Because people are overwhelmed by information.
So there's these great examples of expositors like Serre and Milner and others, and people are affected by seeing this level of exposition and try to emulate it or at least be affected by it. So I think that's had a big influence.
I have a theory that Kervaire-Invariant's theorem is not so well appreciated because Milner stopped writing up topology just before. So,
of course, if Milner had then written a book explaining Kervaire-Invariant,
we would be in heaven.
He had a fantastic influence by his great expositions, and it led people into areas that they might not have gone into. Yeah, or at least it would have been a lot harder for them to go into it. Yeah. Certainly it was the case with me. I mean, their paper on Kervaire and Milner on groups of homotopy spheres was so beautiful and well written and so on. It was the royal way to differential topology.
One of my two supervisors, Andrew Casson, when I started working with him, gave me his copy and said, "You have to start here."
Since I'm serving as an officer of the AMS, I naturally wonder, when did you get heavily involved with the AMS?
Way back when I was in Cornell, and I was just a young squirt, and suddenly I was nominated for the council.
Oh.
I didn't quite understand why, but then I got elected.
You at least made it to president.
Yes.
I was unopposed, in fact. It was an unopposed election when I was elected.
Can you tell us how you've seen the AMS develop over your career?
It's, of course, grown, and the influence has grown, and so on. And I think basically it's kept its focus on research and so on, even when it has more attention to teaching and questions like that. So I don't think its basic nature has changed very much. Of course, technicalities have changed a lot. The size has changed over the years. Yeah.
I understand that they used to have money problems back in the 70s, or...
The AMS did not
yes.
have money problems, I think. No. It was making a lot of money in its journals.
And mathematical reviews, presumably.
I think it's probably harder now. Math reviews was always a big problem. That was an expensive operation. All the other journals made pretty good money, and so that supported the math reviews, basically. But that was always the big issue at trustees meetings, was the budget of the. It was like the budget of math reviews was the big. It was like the defense budget in the federal government. It dominated the discussion. But of course, it was a very worthwhile thing to do. It always had a lot of support. And it's great the way it's developed into the Math SciNet.
Oh, yes.
That's a really fantastic service. So I take my hat off to all those people that designed that and carried it out. That was a very, very far-sighted thing to do.
Do you have any experiences or achievements as AMS president that you want to tell us about?
Well, I was very good at running the meetings.
Keeping them short.
They would start in the afternoon and run sometimes to the wee hours of the morning before I became president. And then I came into one meeting of the council and I said to Secretary Robert Fossum, well, here's my outline for the agenda. We're going to have so much time for this, so much time for that. We're going to adjourn at 10 o'clock p.m. And he laughed in my face. He could. It was such a ridiculous idea, and we adjourned at 9:58, and he had to recognize that. Okay, so it's a little Mussolini-like, I guess.
They made the meetings run on time.
Meetings run on time, but it was a good thing to do. It was really getting out of hand.
Over the years, it became more professionally run organization. And,
It was quite
and
professionally run.
Even then?
I think it was professional, very professionally run, much smaller scale. But the staff of the AMS
Was always very good.
terrific, very, very energetic and dedicated, and it was really a good operation.
I think it has more of a committee structure feeding into the council now than it did at way back.
Well, it had a lot of
But it
committees.
had that already then?
Yeah, that was one of the biggest parts of being president, was trying to find members for all these committees you had to appoint.
Now we have the Committee on Committees.
And we had it then, but then you have to appoint members to the Committee on Committees. and then they would give you suggestions. But
Did the education committee give you trouble?
there wasn't an education committee as such when I was president, but we were getting involved in education. And
But that's a very contentious issue. It's much more than research, I think.
oh yeah. When I was president, we started to get involved in supporting various efforts, like the standards thing that was put out by the Washington Committee about education. And Ken Hoffman was very involved in that. And that was after the David Committee. I should say a lot about the David Committee, because that was my really big achievement.
What was the David Committee?
It began in the late 70s that people began to notice that mathematics was being really shortchanged in the way they were making grants, and they were squeezing the money out of mathematics.
You mean the federal government?
Yeah, I mean the NSF and the agencies, the federal government. And I was at that time the chairman of the NRC board. Was called Office of Mathematical Sciences at the time. And so I went to our parent group, which was the Assembly of Physical and Mathematical Sciences and Engineering, I think it was called. And to this group of physicists and chemists and geologists and so on, I made the case that the mathematics funding situation was really in a crisis. And when they heard the dimensions of a normal mathematical grant, they were so shocked that it was very easy to get them to support a study.
Shocked at how tiny they
Yes.
At how tiny they were. And several people said to me, how can you do research on such short rations? And so we got very good support from this assembly. And so we got authorized to have a committee. And the first step was to hire an executive director, because he's the one that's going to do all the work. And I got Ken Hoffman to do it. And I'd known him at MIT by being on the visiting committee there for some years. And I thought he was a fantastic politician and a really good guy. And so he agreed to do it. And then we got Ed David, who was a former science advisor, I think, to Nixon. I think he was a science advisor to Nixon, and had a very prominent role in the government at one point. And he had been chairman of the math committee at MIT, the math visiting committee at MIT. And so we convinced him to chair this committee, and then we produced a report documenting how badly the mathematics was being funded, particularly compared to all the other sciences. And it had a very big impact, I think, for a short period of time, like any such report does. But it did have an impact at the time. I think, and I would make the case that that was also the turning point to the political involvement of mathematicians in science politics. And I think since then, a lot more mathematicians have been very active.
Well, I think the Vietnam War must have.
Well, but that was a different kind of activity.
Yes, but I think people must have been somewhat suspicious.
Well, there was a lot of discussion about, good money and bad money.
Exactly.
That was a poisonous discussion, in my opinion.
But this is more about policy, influencing policy within the government, right? In terms of funding.
The idea that mathematicians would get involved in trying to influence policy and be active in advocating for mathematics in political realms, that became very standard after that.
I mean, these are all very much current issues. That's to say, the question of what the level of societal and particular government support will be for science in general, but for mathematics in particular, but the concern is, if anything, growing now. It's coming back very strongly because of all the budget issues that government faces here and in Europe.
And much so in the United Kingdom, where
Right. So it's a worry. If anything, these problems have become international.
They never get solved.
And they don't get solved.
That's why you need constant political struggle. And that's what didn't happen in the 60s. And that mathematicians were not standing up for their...
Well, I think they were standing up for other things.
Well, it's also many mathematicians are not as aware as you were of the role that funding plays in the life of their science. They underestimate it because of their own idealism, perhaps.
Yeah, that could be. That could be.
You were also chairman of the math department here at Princeton.
The first year was a learning experience. The second year was a lot of fun, wielding power. The third year was a real drag. Because, all right, we'd done it, and it was a lot. It was the most attention-demanding thing that I ever did, because president of the MS, I go home and sleep at night. The NRC, okay, do that, but being chairman of the department, we're constantly dealing with small problems that people would bring to you. They needed something. There was a conflict between two people or something, and you had to settle it. So when I woke up in the middle of the night, what did I think about? Did I think about mathematics? Did I think about a theorem? No, I started thinking about, how do I deal with this guy and how do I deal with that guy?
Which year were you chairman?
Let me see. I think it was around 71, 72, 73, something like that.
And how were your colleagues? How is the bunch here in Princeton?
Well, of course, I didn't have that much experience with other departments, but it's an amazingly harmonious department on the whole. My experience at Cornell, of course, I was only tenured at Cornell for the last couple of years or so, but we used to have some really nasty arguments in the department meetings, and there wasn't no feeling of unanimity, of coming to a consensus and so forth. It was a struggle. And you win the struggle, you lose the struggle, but there was not a consensus. And in Princeton, it was almost always a consensus. It was the most harmonious department I ever was a part of. On the whole, it's been very harmonious.
And what relations with other departments or the administration?
The administration in Princeton has most of the time been extremely supportive of the math department. They really respect their math department and really value it. And so that's made it easy to be a chairman, relatively easy to be a chairman. I hope that stays on. Sometimes we had quite vigorous disagreements with other departments. We would run a differential equations course for engineers. Sometimes they didn't like it that we would assign a graduate student to teach this course. And once they came to me and objected that last year we assigned this graduate student, and I said, well, it's really okay because this graduate student who was teaching the course is now a full professor in Chicago. That was Charlie Pfefferman, who was, by the way, a great teacher, of course. So that shut them up pretty well. So then they had a little more respect. The other departments are more interested in getting their students into math courses and getting them better trained in mathematics than they used to be. And I think mathematics has gotten much more respect, I think, among the other sciences and engineering than it had 30 or 40 years ago. It felt like something extraneous to their needs, and now I think they can recognize how important it is to them to have mathematical research going on and to be in contact with mathematical research.
Do you remember any senior theses you supervised which were memorable?
And there was a period, 1970 or 71, where I had a whole bunch of students writing senior theses with me at the same time, and Mike Davis and Elliot Stein and,
excellent.
And Steve Weintraub were all. Yeah. So that was a very good year for senior theses.
Yes. Yes.
But I've had a lot over the years.
Yes.
And it's hard to remember too many of them.
You know, I always admired this system here.
Yeah, it's a great system. Well, should I tell you my standard anecdote about what's the difference between a junior paper, a senior thesis, and a PhD? Well, the junior paper, your advisor points out a mistake in the literature and you go and correct it. For the senior thesis, you go into the literature yourself, find a mistake, and correct it. For the PhD, you make your own mistake.
Well, it continues.
That was your problem. That was John Moore's mistake.
But that's it. I mean, the incident with my thesis, and that was a blessing that it fell apart, because it would not have been my thesis in the same way, and I would not have gotten the independence and the self-assurance.
I had the same experience, not quite the same way, but my advisor in the casting told me it was the wrong time to do surgery. You and Terry Wall and so on had all done it. It's all been done. And this is Kervaire Invariant also. And what's left is far too difficult for you. So that really got me excited. But now I see he was right. At the time I was very angry. Now I see he was absolutely right. How do you see the topology now compared to topology, say, 50 years ago?
Wow, it's gigantic. It's gigantic. I mean, all the new ideas that have come in and revolutionized fields, it's unbelievable. I mean, from of course, algebraic topology has been revolutionized in some way. Well, but going back, but three manifolds and Thurston's revolution in three manifolds, Donaldson's revolution in four manifolds, real revolutions that changed Friedman. But the Friedman didn't lead to so much. Well, it really finished off something, and it was very hard to push any further.
In fact, worse. Now trying to reconstruct this proof.
Yeah. It's a fantastically difficult proof, technically. Donaldson opened up a whole new area that nobody knew existed. I mean, it was it's one of the greatest pieces of mathematics of the 20th century, without question. Yeah.
So that's
But I mean, algebraic K-theory and motivic homology and all these things.
Going back to your greatest contribution, of course, was topology of high-dimensional manifolds.
Yeah.
How do you see the present and the future of high-dimensional manifolds?
Well, I think probably it's got to go in more refined directions. Well, a big change came in algebraic topology when we started studying with similar techniques smooth manifolds and PL manifolds. And I think now topology of manifolds has got to move across some border.
To algebraic geometry, maybe.
Algebraic geometry is possible, but new places, new venues to develop algebraic methods. A lot of this algebraic geometry and so on, motivic homologies.
But there hasn't yet been enough crossover. Surgery theory is still looking for a role, I feel.
Surgery theory has not really moved, but a lot of things have been developed from algebraic topology. Yeah.
There's still hope, I hope.
Yeah. Oh yeah. Sure.
People lament the over-specialization to some degree of areas of topology, and the fact that there's no longer the unified whole that maybe existed when you were younger. And I think a student who's starting, it's kind of daunting to know where to start. So what are your views on that kind of process?
Well,
that's happening?
maybe one should view the total of topology the way we viewed the total of mathematics 50 or 60 years ago. I mean, that was a big portion to swallow. You couldn't really swallow the whole thing. And I think now topology is so gigantic that you can't swallow. It's very hard for a student to swallow the whole thing. That's a very bad goal. And you have to really pick out something and concentrate on it. I think it's a natural outcome of this exponential growth. There are many places to start, of course, and say 50 or 60 years ago, there was a few places to start. Now there's a myriad of places to start in topology. Well, you just have to choose. I mean, instead of doing functional analysis, I did algebraic topology. Now they can choose between low-dimensional topology this way, low-dimensional topology that way, low-dimensional topology the third way, algebraic topology in many different forms, algebraic K-theory, blah, I mean, on and on and on. But it's the same problem. It's just our little world has expanded to the giant world that all of mathematics was like, say, 60 or so years ago. So there's no hope for being really on top of the whole subject.
Going back to advising young people, one of the things I remember you doing as a PhD advisor was you tended to have a view of students as being using the right gears or the wrong gears by telling them things like you're working too hard or you're not working hard enough.
that you said that was very brilliant. Yeah, that comparison. Sometimes you put a brake on someone, and sometimes you release.
It's dangerous to start working in an obsessive way without looking around, without relaxing sometimes and seeing what you're doing. So while you do have to be obsessive to do mathematics, you also have to keep a perspective on what you're doing and have a relaxed approach. If you don't have a relaxed approach, you'll miss some important things going by. If you don't look to the left and right.
You have to be prepared to zoom in and zoom out.
Yes. Focus.
Remember, you expressed that once by saying you have to lift your head from the trough once in a while.
That's very good. More likely to have from the mire.
Another interesting piece of advice was, I remember, go read so-and-so's paper. He always leaves meat on the bones.
Very nice.
Now, do you have any advice that you can give to aspiring mathematicians, in the retrospect of your career?
Yeah, my first piece of advice is really don't take anybody's advice too seriously.
Including that piece.
Yes, of course.
There's a lot of really elementary things. You have to get a technique. You have to develop a technique. Once you've developed a technique, then you have to develop a point of view. And you have to figure out what you're going to use your technique on, and you're going to figure out eventually, as you do your research, your own point of view, your own independent point of view. But this is all kind of generic. I can't give anyone specific advice on how to be a mathematician. Maybe a 10-step program how to become a mathematician.
Does it matter whether students do a thesis in a fashionable field or not?
It goes both ways. There's a lot of luck involved in this business. Let's face it. Who was the baseball player? He said, I'd rather be lucky than skillful. Lefty Gomez, I think.
And also Napoleon said the quality he prized most in his generals was the luck.
And it's certainly true in mathematics. Sure. I mean, yeah. But of course, you've got to be in the place where you can use your luck effectively, and that's the crucial thing. Yeah, and that's the technique and the point of view and so on. And then you need a little luck.
Yes.